semiconductor that has a really humongous band gap. So the idea is that, okay, it's really difficult to create thermally excite electron hole pairs across the gap. So it might be like several electron volts. And so that's why they tend to have a very, very high resistivity. And so a good example of an insulator would be, so here's obviously the most pervasive semiconductor is silicon, which everybody's somewhat familiar with. The crystal structure of silicon is actually exactly the same. It's actually called the diamond structure. It's actually the same as the crystal structure of diamond, which is carbon, essentially. And the main difference between diamond versus silicon is that silicon has a band gap, if I remember off the top of my head, I think it's around less than an EV. I think it's like 0.7 electron volts. But by contrast, the diamond, which is normally a pretty good insulator, very good insulator, has a band gap of several electron volts. So it just takes a lot of energy. It's very low probability at room temperature that you would actually excite electrons across the band gap, and then put electrons into the conduction band and leave holes behind in the valence band. Okay, but what about a metal like gold or silver, whatever, copper? So the key difference between a semiconductor or an insulator and a conductor is that in the case of a conductor, remember I talked about the Fermi surface as an example before. I talked about the free electron gas model, fermions. Well, it turns out even in a real crystal, when it's not like a bunch of free electrons, what happens is that the valence electrons, you still have band structure. So even in gold and silver and copper, I mean, you actually still have bands there, energy bands, and you even have gaps and so forth. The key difference is that whatever is the highest occupied band that has electrons in it is only partially filled. In other words, what happens is that band ends up getting filled up to a certain point, but then you have a boundary, and so then that is, in fact, the Fermi surface of whatever that metal is. And so that means that there's plenty of available states into which you can move electrons so that you can end up having a net current flow, like in gold, silver, or copper. And so what this chapter does, now I want to emphasize, it would take at a minimum an entire course on condensed matter physics to really get into all the nitty-gritty details about how do you actually, and more than that, actually, be even more than that, to probably take you to do a PhD thesis topic with one of the world's leading experts on band structure calculations, where you're actually doing band structure calculations as part of your thesis to really get into the details, because the actual process of calculating real band structures of real materials is the sort of thing that, well, and guess what? It turns out that in the old days you had to use a supercomputer for anything, probably even silicon. Now, I think because of the clever techniques plus the much greater computer power that we have today, you could probably calculate the band structure of something like silicon on your laptop. There's actually, I think, a company called it's called Applied Materials that actually does that kind of thing as part of its, for companies that maybe they want to know, okay, what's the property of a certain material, and they'll do things like calculate band structures, they'll calculate other things like conductivity, thermal properties, even mechanical properties of some of the materials. And so they've actually been able to make a living for umpteen employees, I guess, actually doing that kind of thing. And so for something like silicon or diamond, you could probably do a reasonable quality band structure calculation on a laptop. It may not be absolutely perfect in terms of its precision, but it'd be pretty reasonable. Now, for something that's really complicated, like yttrium, barium, copper oxide, where the unit cells are really, really complicated, then I think that starts, I'm guessing that's something that's going to be beyond the power, I suspect, of most laptops, and so that'd be the kind of thing that you start to maybe use a more powerful computer or cluster, maybe supercomputer. The things that are really super complicated, okay, that's where they're presumably going to be using supercomputers to do the calculations. And then clearly there's decades worth of work that have gone into figuring out a lot of the approximations that have gone into figuring out the band structures of these different materials. So again, I want to emphasize, even these have band structures, but the key difference is that the uppermost occupied band is only partially filled, so it's not completely. So, and whereas anything that's, I guess they don't even show the semiconductors here, but oh yeah, they do. Okay, that's diamond. Diamond would be it's actually a semiconductor, but it's also at room temperature. It behaves like a pretty reasonably good insulator. Germanium, silicon, and okay, this must be graphite, because here they're showing it as having a low resistivity and a conduct. Okay, graphite obviously has a different crystal structure from diamond, and so instead of being a semiconductor, it's actually it's a reasonably good conductor. So when they say carbon here, when they show a low resistivity value like that, then I'm pretty sure that they're talking about graphite and not diamond. Diamond is going to be just the opposite. So it's going to have a very extremely high resistivity, even much higher orders of magnitude higher than silicon at room temperature, and obviously conversely a very low conductivity. So let me remind you, I went through kind of a hand-waving semi-classical, well, pretty much classical derivation of conductivity. Let me remind you, how do we estimate conductivity? And then the resistivity is nothing more than the inverse of the conductivity. I'm just going to use, now it turns out that you can actually go and justify this more thoroughly using quantum methods and get more or less the same result as long as you make the right reasonable definitions for this thing that I'll call the relaxation or the scattering time. But just from a classical point of view, let's say you have a carrier, and it's easier just to think of it as a positive carrier, because that way you don't have to worry about fiddling with cancellations of the minus signs and so forth. You get the same result if it's an electron, just that everything is going backwards and all the minus signs end up canceling out. So I'm just going to imagine you have a carrier of charge E that's going over some time period tau. And so the idea is, okay, it accelerates by at some rate A. Now what we really care about is what is the net acceleration along the direction, from a classical point of view, along the direction of your applied field. So let's say your field is going this way, and we're interested in the components. We don't care about other components of velocity. We just care about the component of velocity going along the same direction of electric field. And the idea is that, okay, over some time tau, it takes this amount of time for the thing before it scatters. And again, let me remind you, what are the things that are going to scatter an electron or a hole? It's either going to be lattice vibrations, which are called phonons, and that depends on temperature, so that increases the scattering probability or scattering rate, which is the inverse of this time, goes up as you increase the temperature. Or it could be impurities that could scatter this guy, getting from point A to point B. So you have a really pure material, and if you cool it down quite a bit, then in principle this time should start to go way up right here. It's also, this time is related to what we call in semiconductor classes. If you take one in electrical engineering, this turns out to be very closely related to something that's called the mobility of your material, like your semiconductor, for example. So at any rate, if I say, okay, F equals MA means that A is equal to F over M. If I say now, just as a rough guesstimate, and I don't worry about factors of a half, I just redefine the constant as needed. If this thing is equal to, in other words, it accelerates over some time period, and I say, okay, the drift velocity along that direction is about equal to the acceleration times this scattering time, t. Okay, so what is that guy? That's going to be equal to F over M times tau, not t. And that, remember, F is just equal to the elementary charge little e times the electric field E. So you have E times E over M times tau. Okay, so that's our drift velocity. And so then let me remind you that the current density, current per unit cross-sectional area, is the number of carriers per unit volume. So that's typically written as N times the charge, E, times the drift velocity. And so if I do a bit of algebra, put these two together, what does that give us? That gives us N E squared tau over M times E And by definition, we say, okay, that's equal to sigma times E. And so you can see that, okay, we end up deriving with a few lines of algebra, we end up deriving this expression that the conductivity of your material is NE squared tau over M. Now, in reality, what's going to happen is that when you include the band structure of the material, this thing, which again, if you take a class on semiconductor physics, gets replaced by this thing that's called M star, and that's called the effective mass. And that, again, it just depends on the curvature in your energy versus momentum curve, or energy versus K curve. And so if it was a free electron, or nearly free electron, then that would just be the electron mass. So like in gold, silver, or copper, this is probably just about equal to the electron mass right here. Okay, so now that gives us a pretty good clue as to what to look for when we're trying to estimate, okay, how big should the conductivity, and again, let me remind you that the resistivity, rho, is just 1 over sigma. So that's the resistivity right here. And then this, of course, is the conductivity. And so the idea then is, what is the relevant value that goes into N? That is going to be the number of, I guess you would call it conducting, I'll call it conducting electrons. These are the ones that are in that uppermost partially filled band, the number of carriers that are actually available to contribute to the current. So the idea is that in the lower bands, and we'll be leading up to, okay, what are these bands roughly, what do they look like, coming up here pretty soon. But the idea is that any filled band, they're basically trapped. In other words, you just cannot get a net current flow in those filled bands. So it's only the partially filled bands at the very top, they may not be the very top, but the upper, in other words, the uppermost occupied bands, if they're partially filled, only those guys can contribute to the net current, essentially electrical current. And so those carriers are the ones that are relevant for estimating what is this number of carriers per unit volume right here. And so in the materials like gold, silver, and copper, this number is big. So if I remember off the top of my head, I think it may be like in the range of some number times 10 to the 23rd or maybe 10 to the 24th electrons per cubic centimeter. And then of course if you convert that to cubic meter, per cubic meter, it'd be even bigger. And then this is related to the mobility. The mobility is pretty good as well. I think in those materials are quite good. So, which in this scattering time, I don't remember numbers off the top of my head, but let's say we could kind of estimate backwards, I guess, to try to guesstimate what that would be. And then in those materials, this would be about equal to the electron, close to the electron mass right here. And so at any rate, it's because they have a high carrier concentration of light mass involved here, and then probably a good scattering time, that these materials have very, very high conductivity. So you can see if you go to inverse ohm inverse meter, something times 10 to the 7th. So silver is up here, and then copper, and so on and so forth, and aluminum. That's why copper wiring it's not super duper higher, but it is high enough that copper wiring is actually somewhat better than aluminum wiring. It's more expensive as well. It's also, people tend to like to steal copper these days as well, apparently. But at any rate, you can see, okay, copper is better than aluminum, and tungsten, you're going down somewhat, but tungsten is actually, for the old-fashioned incandescent light bulb, which is starting to become somewhat obsolete, but not completely. The idea is that you're using the finite resistance of that material to generate the heating, the I squared R heating, that allows the thing to glow white hot and actually give you light coming out of a tungsten filament of your incandescent light bulb. Now, I was actually surprised that platinum's actually way down here. I thought it was actually better than that, so apparently it's actually even not quite as good as some of these other materials and whatnot. Now, interestingly, these are really good conductors, but none of them become superconducting. So it's rather interesting, kind of ironic. The first one on this entire list that I don't know if tungsten does, aluminum actually is the first one on this list that I know of that does become superconducting, but it's only way down, I think around 2, maybe below 2 degrees Kelvin, or somewhere in that range, 2 degrees Kelvin, or 2 Kelvin, I should say. Platinum is non-superconducting, I don't, to my knowledge. Lead is actually superconducting around 7 Kelvin, if I remember correctly, somewhere in that range. And now, so insulators. So the idea here is that in principle, so this is at room, I assume these are at room temperature, yeah, 293 Kelvin, so that's about room temperature. Again, the idea is that rubber is not even a nice crystal, so you couldn't even really define a nice clean band structure, but for anything that would be very similar to that, let's say if you could create it in a crystalline form, the idea is that any bands, any upper bands would be completely filled, and then there'd be a big band gap, presumably, going from the, we'll say the valence band up to any potential conducting bands. And so quartz, that is a crystalline material, because I think that's aluminum oxide. So I think that is a crystalline material right here. And so you can see, okay, that's a really good insulator at room temperature, but the idea is that it's because it's a really, in principle it would be a semiconductor, but the band gap is really humongous between the conduction band and the valence band. So at room temperature, there's hardly any carriers excited across the band gap at room temperature, and that's why you have such a humongous resistivity. In other words, the conductivity goes way down because N, the number of carriers that are able. So what happens in a semiconductor is that the number that goes here would be the number of carriers in the upper conduction band. And if it's just an intrinsic semiconductor with no doping, with like no electrons or holes or donors or acceptors, that number N is just the number of carriers that are, most of the time it'll be the number of carriers that are thermally excited across the band gap into the conduction band. And so that's clearly going to be a function of temperature. In fact, N, I'll just say I'll just write it down, in a semiconductor, N is going to be proportional to E to the minus band gap energy divided by KT. And so the idea, and that's because you have to overcome that energy gap, so E sub G is the energy gap. And so you have to overcome that to thermally excite these carriers. And so what's going to happen then is that as you go down in temperature, the conductivity goes down, or the resistivity starts to go way up. As T goes to 0, then this thing starts to go down to 0 right here. And so the inverse of this thing starts to go way up. The resistivity will start to go up as you go down in temperature. And this is called thermal activation, in a thermally activated form in the case of a semiconductor. Okay, room temperature. And okay, so it's later just in principle, it's a semiconductor that has a humongous band gap. And so in semiconductors, well, so you have to either excite carriers across the band gap, or you have to dope them with donors or acceptors. So you're creating, that's a whole, I don't know how much we will be getting into, if we'll get into that at all, but if you take a class in electrical engineering on semiconductor devices and physics, then they would teach you about, presumably about doping P-type and N-type semiconductors, in which case that expression on the right, would, or that curve on the right, would not actually apply. So I hope I have this correct. So on the left, okay, conductor at low temperatures, unless it's a superconductor, in which case this thing would actually come down and then boom, it just suddenly drops down to 0, but below some critical temperature. semiconductor. So if I can remember, okay, so if you remember that, let's see if this looks. I think this looks right. Yeah, the idea is that, okay, so if this goes as e to the minus Eg over kt, that means the resistivity. Oh, and conductivity, of course, is proportional to n. So the resistivity is going to be inversely proportional to n. So it's going to go like this. And so that means the natural log of resistivity is going to be proportional to Eg over kt. And so that means that if you were to plot log of rho versus 1 over t, or 1 over kt. So as t goes to 0, rho goes up, so I think it would go like this. It would actually be a straight line. Okay, and the slope is proportional to the band gap, is the idea. So in other words, you could infer the band gap by looking at the slope, how steeply. And so conversely, when you go down in temperature, right here, the bigger the band gap, the more steeply it's going to rise up in the, as you go down in temperature. And this is called an Arrhenius plot. It's named after somebody by the name of Arrhenius. How do you spell that? I think he spelled something like that. So this is for a semiconductor, in other words. Intrinsic, not undoped. Intrinsic semiconductor that has not been doped. And so the idea is that at any given temperature, the conductivity, which is the inverse of rho, is really going to depend on the number of carriers that have been excited across that band gap, so that you have a finite number. And let me draw a little diagram without putting in the band structure. I'm just going to kind of do it the way we typically, or people typically do it in electrical engineering, where oftentimes they care just, okay, because a lot of times you're going to be drawing band gaps that are changing, like in your p-n junction versus position. But oftentimes you'll just represent this to represent the conduction band. No, I'm sorry, I got it backwards. This is going to be the valence band right here. This is going to be the conduction band right here. And then what you will do conceptually is you'll say, okay, I'm going to think of this guy as being a hole right here. When you excite, thermally create an electron-hole pair, and then this will be your electron across here, and then this will be the band gap right here. And so the idea is that at room temperature, or at any temperature, if this is, by the way, you can still define a Fermi level, and that Fermi level is typically, if it's intrinsic semiconductor with no doping, that Fermi energy is right smack in the middle of that band gap. And so if it's doped, it could be either way up here or way down here, depending on whether it's N-type or P-type. And so the idea then is that the number of carriers that I'm referring to is how many electrons, and it'll also be equivalent to how many holes as well, but we'll say how many electrons have been excited across that band gap and so N would be, that would give you the number N right here, so it'd be a strong function of temperature. The mobility in semiconductor device physics or engineering would be directly proportional to this guy, tau, right here. So in semiconductor devices, and then I don't want to get into, I forget exactly the precise definition of mobility, but it's proportional to this guy right here, tau. And so that's, so the mobility, so the idea is that the conductivity is proportional to the number of carriers per unit volume times the mobility. So the mobility may actually end up being something like, it may be like E squared tau over M, or I don't remember the factor of E squared is in there, or E is in there, I don't remember. But it's proportional to tau over M. And so that means that the lighter the effective mass, by the way, you replace M with M star, the effective mass, so the lighter your effective mass, then that's another thing that will increase your mobility of your semiconductor device or material. Okay, band theory, energy gaps between the bands. So then they first started talking about in the context of hydrogen atoms or any atom, where the wave function have hardly any overlap if they're very far apart. But then if you start to bring them together, the idea conceptually would be, well, I start to have to solve the Schrodinger equation for my potential that includes both of these ions. So think of this, in the case of hydrogen atoms, that'd just be protons, but in a more general case, that might be the ion, like the sodium ions, if you're talking about sodium, or silicon, just including only the outer valence electrons, and then the rest would be the core electrons of your silicon atoms in that case. And then in the case of like a hydrogen molecule, H2 molecule, you can have a symmetric combination of these guys that gives you a wave function that looks something like that, or you can have an anti-symmetric combination. And then there could be some energy difference between these two states that sort of represent this combination of these guys right here. And so that would be kind of a rough idea of where would a band gap sort of start to emerge. If I, instead of having two of these, suppose I had a chain of millions of those guys, let's say in a row, for example. You just had a one-dimensional chain. And so as a matter of fact, one of the things that does happen, so we skim over, like I say, decades worth of work in like just a few lectures. So that's why we can't get into too many details, just try to give you at least kind of a flavor for what happens. And so the idea is that when you start to bring things together, by the way, you can also, there's a section in Feynman where I think he does it for maybe ammonia in terms of this thing that's related to this tunneling Hamiltonian matrix element. You can also analyze it using that picture. That would be like a variation of what's called the tight binding model of band theory. And the idea is that you have these energy levels that would be the particle in a box. For example, you start out like with your particles in a box. That might be the easiest one to think of. And if you have a bunch of boxes lined up in a row and you start to bring those together, if you brought two boxes together, maybe this could be my next part of my next homework set that I could assign, then what would happen, and then use a tunneling Hamiltonian matrix element to couple the states across the energy barrier, what would happen is that for two boxes that are separated, let's say widely separated, you just have your original states like that. So this would be like a tight binding model. It's called the tight binding model. So I have my original states like that, but now I bring two of these guys together. Until finally there's only a finite barrier. So what happens is these start to split, and the amount of splitting, let me make this a little higher right here. The amount of splitting between these levels, if I remember, ends up being something like 2 times the matrix element. So let's say T equals tunneling matrix elements or something like that. So these would be the original energy levels we had before for the particle in a box. And now what happens is these get split. And so then the idea conceptually is that, okay, if I go beyond 2, if I start to have n of these guys in a row, so I have n boxes, so now it's a bunch of quantum wells. By the way, those are actually used, I think, in the laser pointer, as a matter of fact. I think they use a whole mess of quantum wells, I believe, to give you some narrow, I think basically the idea is to try to create narrower bands so you have a sharper band gap, I think is the idea. I should probably pull out my laser pointer at this stage. so if you have, and the way they do it is they actually create alternating layers of gallium, maybe gallium arsenide, gallium aluminum arsenide, or some combination where you're changing the, actually the band gap of the, well, basically between the conduction band, this will be the conduction band, and then the lower valence band. So you're changing the band gap versus position. So it's like a bunch of particles in a box. And so if you have n of these in a row, say they're brought together, something like this. I'll try to, I didn't do a very great job, but what'll happen is that instead of having just splitting between into two levels, you have split, each one of these splits up into n levels. I should probably make these a little higher, I guess. So each of these guys splits up into n levels into a little band. It starts to become a band, essentially. So this would be like the lower, so this would be the way bands would come about in a model that's called the tight binding model. And actually that's a good way to describe, particularly like the core electrons and your even in silicon and things like that. Now there's another model, the Koenig-Penny model that will, I think this book talks about, maybe more close, I'm not sure which one's closer related to it. There's one called the nearly free electron model. So the tight binding model is one of the models that was used in the early days and still used even now in a lot of contexts to describe, okay, how do bands emerge. There's so another one called the nearly free electron model, kind of going to the opposite scenario. Or NF, oh, this could also be called TB model, I guess. Same as tuberculosis, I suppose. Okay, NFE model right here, nearly free electron model. And so in the nearly free electron model, the idea is that what you do is you imagine, okay, I have this these energy wells that are potential wells that where the depth and the heights of great job here. Well, maybe it's good enough. The heights and the depths of the wells is relatively small, let's say, compared to the energy of your electrons. So the electron's sitting there zipping along, and what these do is these sort of cause reflections in some degree of reflection and interference, essentially, of the electron. So it's moving along, zipping along. So the wave, so you can describe it roughly as e to the ik, some wave function that looks like this times some other function of x, I suppose. Psi of x, maybe the wave function. So it's sitting there zipping along, and so it's essentially, it's weakly perturbed by this periodic potential, is the idea. And so in the nearly free electron model, you sort of think of this in a to some extent, you can think of it perturbatively, but then what happens is right at the band gap, you end up with showing that, okay, a band actually opens up. So the nearly free electron model, if I plotted energy, so I think the Koenig-Penny model will be, that we'll talk about, that's in the book, will be a little, probably more close, will be closer to the nearly free electron model. So the idea is that I start out with my original energy versus, I'm sorry, this is supposed to be versus K right here, K. So originally we had h bar squared K squared over 2m originally, like this. And so then what happens is that you say, all right, Now, because of this extra periodic potential at certain points, which will turn out, so if this spacing is A, if I remember correctly, then what's going to happen is that when for certain values of k, where let's say k is equal to pi over a, this is b minus pi over a. I think the next one is going to be at 2 pi over a, I believe, if I remember correctly, and so on and so forth. Same thing on the other side, minus 2 pi over a. You end up, because of this extra scattering that takes place of the electrons, right at these points, you end up with the gap opening up. And that is, and the value of that gap, I think ends up being, if this, in other words, the idea is that we imagine that this amplitude, it might be, you might think of your potential as being a nice simple sine wave, like V of x is equal to V naught or V1 times 1 minus the cosine of, I'm not sure if it'd be 2 pi x over a, or some, some function where the wavelength would be a, essentially for that periodic potential V. So V of x would be something like V. I think it's going to be V1, maybe times 1 minus the cosine of, and I think it's 2 pi x over a or something like that. And the idea is that what happens is that, okay, we imagine that V1 is going to be small compared to some of the energies that are relevant when you're in this h bar squared k squared over 2m region here. And so then the size of the gap, when you go through and apply, I think you use